Hi friends, a very good evening and thank you for joining in today. Could you please confirm in the chat window if you are able to see my screen and hear my voice so that we know that there are no technical glitches whatsoever and we can start the session itself. Could you please confirm that? Again, there are a couple of general questions. So the first question is about syllabus for graph theory. There is no change whatsoever. There might be small change in the wording, but there is no change at all. So whatever you learn for graph theory in discrete mathematics and data structures and algorithms is sufficient for the GATE syllabus. The next question is for graph theory, there are so many terms. How do you remember them? Again, the simple mechanism is we have already done a session on how to prepare short notes. So we provide you publicly available handwritten detailed notes. Try to make short notes based on that and revise it. It's very easy to get confused with terminology because the syllabus is vast, right? So this is true not just for graph theory, for any subject. GATE, the hardness of problems is never a concern. It is not a race against time. It is mostly about the vast breadth of syllabus, which is what is the biggest challenge for GATE. So the best way to remember terminology or to remember equations or to remember concepts across all of these 50-odd subjects is to revise. Again, we have done a couple of videos which are publicly available on our YouTube channel. So doing that will be helpful. Okay. So Rajesh, I think you asked the same question in the last session also. I mentioned the same thing. We'll be doing a public session, general Q&A session next week. There is no point repeatedly asking the same thing because we already clarified it to you in the last session itself that we will do one next week. Cool, sounds good. So Anirudh, we have a forum for GATE students through which you can communicate with all the students. So feel free to communicate with everyone there, or else just shoot an email, we'll help you with that. Okay, so anyway, as we wait for other students to join, there is one more very good question from Alpan. He says he's facing problems in solving lengthy questions from OS and CO. Again, whenever you encounter a lengthy question, most likely the question is easy. You just have to translate that question, read it carefully and draw the respective diagrams. Today I'll show you that. Very often COA feels hard or OS feels hard. Typically system subjects feel hard because you don't translate the lengthy question into diagrams. The moment you convert everything into diagrams, things become trivially easy. Okay, so let's get started. It's already 7:02. Couple of quick announcements. Again, people have been asking us about DLD content. I think we responded to some of the messages in the chat also. We informed in the previous session itself that the DLD content has been redone by me as per students' requests. So it's already uploaded, it's available. Please go through it. So next week we'll have problem solving sessions for digital logic design. Next Wednesday and Friday. Just giving you a heads up. Again, we'll do an announcement on YouTube with the exact syllabus for these. Number one. Number two is all the new content. For OS, there is a little bit of content about system calls. While we covered most of that in the previous videos, we thought we'll add some more content, right? Similarly, this is not CO, sorry, this is CD, my bad. Sorry. Okay, I was thinking CO when doing this, my bad. So this is CD. Okay, there is some syllabus for CD. Even from the new syllabus of CD, some of it is already covered in our course videos. The additional few concepts that are left. And general aptitude, there is some new, there is significant change in general aptitude. We are already creating notes and started doing some of the videos for this. Our ETA or expected time of completion is 31st August. For example, imagine the moment we complete OS, once we complete any subject, we'll send an email to all of our course enrolled students, right? Similarly, once we complete CD, we'll send an email. So we'll be doing OS first, followed by CD, because OS has the smallest number of changes, followed by CD. Finally, we'll be doing general aptitude. Okay, cool. Sounds good. So these were a couple of announcements that we wanted to make. So let's get started with COA. This is the final session for COA, and this is mostly about memory and little bit about IO, right? So cool. Let's get started. Okay, here comes the first question. Okay, some of our other teammates have also joined. They're also answering questions. Again, this is an easy question. If you know set associative cache, please draw diagrams. The reason most people make mistakes is because they don't draw diagrams. Again, please try to tackle these problems, and we want to focus your energies and time right now in this interactive session on solving the problems. Any questions you have, please go to gate.appliedcourse.com. We have our phone numbers and email addresses. Reach out to us. Please try to solve the problems. Additional questions you may have, you can always reach us over email. The objective of these interactive sessions is to practice and solve problems. Guys, read the question very carefully and draw diagrams. Okay, I see various answers here. The question says, how big is the cache in kilobytes? Okay, so we want a single number, which is the number of kilobytes. Oh, I see like various answers in the chat window. So it's just a number that you have to fill. Okay, and the number should be in kilobytes. Again, I see students doing tons of trivial mistakes here. I mean, there is a wide spectrum of answers. So please draw the diagrams. If you draw the diagram, if you know the concept, this question is an aptitude question. Okay, I see a lot of students doing mistakes. Please draw the, I can't emphasize this. For all the questions we have today, if you draw the diagrams, if you know the concept, they are trivial. Again, this topic in COA is very, very scoring because the questions are often easy. But if you don't draw diagrams, if you do silly mistakes, or if you don't know the concepts, you will mess it up. I see like crazy. I see like, wow. I see 128, 512, 1024, 4 kilobytes, 128 megabytes. Wow, this is like really, really wide spectrum of answers. Again, I see people doing really crazy, silly mistakes. Please draw diagrams, guys. Please draw diagrams. Again, there is somebody who's interested in joining the course. Please visit our course page, which is gate.appliedcourse.com. There are phone numbers, email addresses there. Please give a ring and our team will help you. But please try to watch the free videos before you enroll. We strongly recommend that. Okay, somebody says 28 KB. Wow. Wow. Oh, so the whole memory itself, the whole cache itself is 28 KB. Okay. Okay. Guys, after seeing these answers, most likely what's happening is you're not drawing diagrams or you don't know the concept. You came ill-prepared or you did not revise before coming to this session. These sessions make a fundamental assumption that you've gone through these concepts, you know these concepts and you've revised them. Otherwise, you'll not be able to solve them. Right? So again, the objective of this is trivial. Come on, somebody says very tough. Utsav, come on, you're joking, man. You are in August and this is actually, I should have said trivial question. Come on. This is easy. This topic is extremely scoring. If you cannot solve this problem, I think you're not preparing the right way. Please stop saying this is very tough question. It's a joke. If you can draw the diagram for set associative memory, this will take 30 seconds. I can get a 10th class kid solve this problem by explaining them set associative cache. Come on. Stop saying this is very tough. Okay, so people are solving the questions. Again, this is easy, guys. I mean, this is what you can expect for 1 mark in GATE. Okay, so, okay, let me answer this. I think, okay, see, there are 3 mistakes. This is a first problem. And I'm surprised that people are making so many mistakes. Most likely, most of you came ill-prepared or did not revise. Some of you got the answer right, obviously. I respect that. But some of you came ill-prepared or you have some serious misunderstandings. Draw the diagram. What do you have? You have an 8-way set associative cache, right? This is your set associative cache, right? So you have sets, right? This is your set 0. I mean, draw the diagram first. You have set 1, right? So on and so forth. How many sets does it have? 4096 sets, right? So this is set 4095. So total of 4096 sets. In each set, how many do you have? This is a set associative memory, right? In each set, you will have 8 entries. Right, because it's 8-way, so there are 8 lines, right? So 8 blocks can be stored here, right? So that is what it is given. Okay, of course, this is your tag, this is your line or block, depending on, some books call it line, some books call it block. Okay, now what is the question here? The question says the word size is 32-bit words, right? So one word is 32 bits. So what is 32 bits? It is 4 bytes, right? Simple question. And there are 4 words per line. Look at this, per line, which means per block or per line, there are 4 words, right? So how many do you have per, okay, let me write it down here. 1 second, let me change the color here. So one word is 4 bytes. So what is 4 words? 4 words is 1 line. 1 line or 1 block is 4 words. What is 4 words? It is 16 bytes because 1 word is 4 bytes. It's a simple aptitude problem, no? Then how many sets do you have? You have 4096 sets, right? So how many, what is each set? It's an 8-way associative set memory, right? So the size of this, look at this, the size of this thing, the size of each line is, 4 words or 16 bytes. You have 8-way set associative memory, right? So let's look at it. You have 8-way. So 8 into 16, one set has these many bytes of memory, right? One line, or sorry, one set, I'm sorry. So now let's write for one set, how much do you have? 8 into 16 bytes, right? So now for 4096 sets, how much space do you have? It is 8 into 16 into 4096 bytes. Now what is this? This is 2 power 3, right? So this is 2 power 3, this is 2 power 4, this is 2 power 2 into 2 power 20, right? This is the total thing. Now what is this? This is 4, 5, 6, 7, 8, 9, 29, 2 power 29 bytes. Now the question says you want it in, sorry, not 2 power 29. I think I messed it up. Did I? No. So 2 power 29. Yes. So this is right. So the question says 2 power 9 into 2 power 20. 1 kilobyte. Look at this. You have 1 kilo, right? 1 kilo is 2 power 20. So it's 512 kilobytes. So the answer is 512. Again, if you draw this diagram, right, it's a straightforward question. You just have to read the question carefully. You just see what is one word. One word is 4 bytes. Okay, there are 4 words per line or per block, which means one block contains 16 bytes. Now you have one set. Go from lowest granularity to the highest granularity. First you computed word, then you computed block, then you computed set, then you computed the whole cache. That's it, 4 steps. Of course, if you do it, if you know this diagram, again, always draw diagrams, guys, right? One second. I think I made a mistake somewhere. Did I make a mistake? Sorry. My bad. So this is my bad. I'm sorry. Sorry. My bad. I made a small mistake here. So right. You're right. So 2 power 29 bytes. 2 power 29. 2 power 10 is kilo. I'm sorry. Not 2 power 20. So you have 2 power 19 here, right? That's what is left, right? So this is kilobytes. What is 2 power 19? 2 power 9 is 512. And 2 power 10, right? 2 power 19 into 2 power 10. This is your answer, right? Of course, you get 2 power 10 is 1024, right? Into 512. This whole thing will be your answer, right? So that's it. Sorry, not 512. My bad. Right? Okay, one second. I think I made a mistake somewhere. 1 second, because my answer is correct. I got confused by what some of you are saying. 1 second. I got carried away. 1 second. Let me do it. Let me do the math again. I'm sorry. Let me do the math again. My bad. I did it correctly on my notebook. Sorry. Okay, I got carried away when somebody said this is a tough question. I shouldn't get carried away by comments. Okay, this is 2 power 3. Let me write this down. This is 2 power 4. This is 2 power 2 into 2 power 10. Okay, 2 power 10 is 1024. Sorry, 512 is the right answer. My bad. I should not get carried away by comments. Okay, so this is 4, 9, 2 power 9 into 2 power 10. Okay, so that's right. It's 512 kb. Sorry, not the other way around. Okay, so I read this incorrectly. So 512 is the wrong answer, right? So 512 is the right answer. 512 kilobytes is the size of the whole cache. I'm sorry, my bad. I wrote till here correctly, then I made a silly mistake in converting 1024 as 2 power 20. My bad, sorry. Okay, but this is a straightforward question, right? Okay, this is like literally straightforward. So 512 is the right answer, and it's not a hard question. If you draw the diagram and if you don't do silly mistakes like the one that I have done, this is a straightforward question. Okay, sorry, I made a silly mistake. Cool, let's go to the next question. And I'll not get, like, I got really angry when somebody said, this is a hard question. Come on, you're joking or you're not prepared. Stop saying that. Okay, sorry, I should just keep my cool and solve. Okay, cool, sounds good. Sorry, apologies for that mistake, guys, earlier. So 512 is the right answer for the previous question. Okay, I'll keep cool. Happy. Thank you, Utsav. Thanks. I hope you understood the importance of diagrams. You draw the diagram, it's easy, guys. Somebody is asking about the forum. Just email us. I'm sure you're added to the forum. Just email us. They'll share a link and you can find it on our website also. So please participate in that. This is also an easy question, guys. It's more or less straightforward. If you know how to, again, you'll see a lot of questions from set associative cache because it's the trickiest of all. If you know set associative cache, because it's the most complex, most questions in GATE actually come from this topic. Okay, good. I'm happy enough. I see people putting in the answers. I'm happy that you're drawing diagrams. We have a lot of questions on set associative cache because it's the most asked concept. So draw the diagram, guys. I see people putting in the answers and I'm happy that for the second question, we are getting good answers. Good. Yeah, all of you are putting in good answers. I'm happy about it. Good. Please draw the diagram. That's all is the trick. Then it's a simple aptitude problem. I'm very happy now. I'm very happy to see students doing the right thing now. Very happy. Just draw the diagrams, guys. Ronak has a question about will GATE be removed because of the new NEP? For the new NEP to take hold and to be actually executed will take years. By that time you would have 5-6 years of work experience, so don't worry. Okay, most of you got it right. I'm very happy. This is also an easy question, guys. Okay, so let's solve it. Again, I'll try to avoid silly mistakes. And please correct me if I make a mistake. Let's solve this. What does it say? It says it's a 4-way set associative memory. Okay, again, draw the diagram first. You have your set 0, okay, set 1, okay, it's 4-way, which means there are 4 in this, right? Cool. So you always have tag and you have your block or line. okay, depending on whichever book you are reading. Okay, with so the set associative cache memory has a total capacity of 16 kilobytes. Okay, four-way set associative with a capacity of 16. So the total size is 16 KB. This total size is 16 kilobytes. Okay, is built using a block size of 8 words. Okay, so each block is 8 words. Okay, each block here is 8 words. Okay, the word length is 32 bits. Okay, so one word is 32 bits, right? What does it say? One block. Okay, one block. Okay, one block is 8 words, right? That's what is given. Again, whatever is given, write it into equations and diagrams. Then we'll not mess it up, right? One block is 8 words. What is 8 words? Each word is each word is 32 bits. Okay, which is 4 bytes. So one block is 32 bytes, right? Till there, everything is clear. Next, the word length is 32. The size of the physical address space is 4 gigabytes. Okay, we'll come there. What is the question? The number of bits for the tag field. Okay, so to determine that, how many cache lines will we have? Number of cache lines. Okay, or cache blocks. Okay, number of cache lines. The total size is 16 kilobytes. Okay, and one block is 32 bytes. Right, one block is 32 bytes. So now, if you divide this by this, you get 512. Right, so the total, so there are 512 blocks or that 512 cache lines, but this is a four-way set associative. So how many sets are there in this? How many sets? The number of sets is 512 by 4. So there are 128 sets. Okay, so we got all the information about the set associative memory. The second part here is you have the physical address space, which is 4 GB, right? So your physical address space is 4 GB, right? Remember, you have 4 gigabytes as your total memory, but each word is 4 bytes. So your actual memory is actually your whole memory, while it is 4 gigabytes, it is only 1 giga word. If you convert it into words, because each word is 4 bytes, the total size is 1 gigawords, right? 1 gigawords require, so what does this imply? This implies giga is 2 power 30, right? So these many words, which means your physical address will be 30-bit long. If your whole memory is word addressable, let's talk about word addressability, right? Sorry, let's talk about, where is it? Each word is 32 bits. Let's assume, because you're given a non-8-bit word length, everything is word addressable. So you get 30 bits here. Now let's start filling in the concept, because it says the number of bits in the tag field. Okay, let's break it into 3 parts. The first is offset, we know this. Then you have then you have set, in set associative, then you have the set number, then you have the tag. These are the 3 pieces that you have. So let's start filling in the details now. What is your offset? Again, I'm trying to explain slowly so that people understand it. This can be solved very quickly. Okay. So what is your offset? Your offset basically says, so in one block you have 8 words, right? You have 8 words, which means you need 3 bits, because we're talking about word addressability, right? So 3 bits are required for 8 words. Okay, number 1. How many sets do you have? You have 128 sets, right? Which means you need 7 bits for the set number or the set index. So these 2 are taken away. So you're left with 20 bits for tag. So the answer here is 20. Again, I'm explaining it slowly, but this problem can be solved in like 1.5 minutes if you know the diagram. I'm just trying to explain it and write everything. Again, in exam, because it's not a subjective exam, you don't have to write every line like this, right? You don't have to write every line, but I'm just explaining it in more detail for you, right? Sounds good. Okay, cool. Let's go to the third question now. Okay, this is a good question. This is somewhere between easy and medium. Okay, thanks to the rest of the team. I think they're also answering some questions here. Yeah, these questions are not from test series, guys. These are additional questions that we are setting up so that students have ample practice. These are not our existing questions. Again, draw the diagrams. Even if it takes time, it's okay. Please draw the diagram. Okay, people have started putting in the question. Again, there is a faster way to solve this problem and there is a slower way. It's okay. Take your time and think about it. Draw the diagram of the cache. That's very, very important. I can't emphasize that enough. This question can easily be modified to make it medium. Again, guys, please draw the diagram. It's okay to take time. I see some of you making mistakes. So it's okay to take time. Just draw the diagram, please. Figure out how many bits are there for tag, for set. Break it down. Again, there are two ways of solving it. There is a faster way and there is a slower but a more detailed way. It's okay. You can pick any one of them. I'll try to explain both of them. First, I'll explain the slower approach. Then I'll apply the harder approach. Yeah, all these questions are not original questions. They are based on previous questions, textbooks, etc. We do not guarantee that the questions that we give in these public sessions are original. Only our test series questions, in the sense of our mock tests, everything will be completely original. So here we don't guarantee that it's original. I think this is based on a previous problem. Yes. Because setting up original questions takes a lot of effort. Okay, I see thankfully that some of the people who made silly mistakes are correcting their answers. That is good. It's okay to take time. I'll teach both the ways. When I solve this, I'll teach the lengthier way and the faster way to solve this problem, so that, because conceptual understanding is important. Okay, guys, C is the right answer. Most of you are right about it. Some of you also said D, which is incorrect. So let me show you the more detailed way of solving it first, so that if this question is slightly modified, right, we can easily modify this question and make it hard, by the way. Okay, first let's draw our whole system. Okay, first and foremost, these are the, so 0, 5, 3. So let's write down the whole system, right, first. So let's assume this is our memory. Okay, this is our cache. I'm sorry. We have our tag, right, and we have our it's a set associative, two-way set associative, right. So this is set 0, this is set 1, there are set 2 and set 3, right. So it says the memory has 4 sets, right. So set 0, set 1, set 2, set 3, and it says it's a two-way set associative. So there will be 2 entries here. Let me just try to use a different color. There will be two lines in each set, right. So there will be 2 lines in each set. Let's draw the I'm walking you through a more elaborate solution. Okay, I'll tell you the shortcut also later, but let's first solve it thoroughly. Okay, then what does it say? A total of 8 cache blocks. 1 second. So okay, there are a total of 8 cache blocks. That's expected. Okay, and main memory with 128 blocks. Okay, the main memory has 128 blocks, 0 to 127. Cool. What memory blocks will be present in the cache after the following sequence of memory block references if LRU policy is used, okay, for cache block replacement? Cool. So now first thing that you have to realize here is, look at this, you have 0 here. Look at this. So if you look at your address, right, you have your offset, right? then you have your set bits and you have your tag bits. Okay, it clearly says that there are a total of 128 blocks in the main memory, right? So which means this whole thing will be 7 bits. This address part will be 7 bits. Then there is some offset. We are not told how many bytes or how many addressable words are there in each block. That we don't care about because you are given the block numbers, right? So this requires 7 bits. Now, if you notice, how many sets do you have? You have 4 sets. So the set will be only 2 bits. The tag will be 5 bits. Okay, that's the important part. Now look at this. You are given 0. Okay, so let's try to write 0 into this whole form. Okay, 0 is 5 zeros and double 0. Okay, this is your 0. This is your block 0. Right? This is your block 0. So where will this get placed? Again, look at this. This will get placed. The set is 0. So here you will have 5 zeros and 0 will be placed here. Again, I am drawing this diagram here because this question can easily be changed and said, hey, in set 2, what all entries are present or what all blocks will be present? We can change this question slightly and make it slightly on the trickier side by saying, hey, what all entries are present in set 1 or set 2 or set 3? Right? I'm explaining it slowly. I'll tell you the faster solution in a few minutes. Then you have 5. How do you write 5? 5 is 0, 0, 0, 0, 1, 0, 1. This is 5, right? So this goes to set 1. So it will go to set 1, 0, 0, 0, 0, 1. So 5 will be placed here. Right? Sorry. So one second. What is the second entry we got? We got 5, right? Yeah. So 5 will be placed here. Next, let's see. Let's see what happens. Okay. So 5 is placed there. What is the third one? We got 3. Let's go slowly because I want you to understand the concept here. 3 is 0, 0, double 1. Right? So in this setup, what do you get? This is this. So where will 3 go? 3 will go into set 3. So 3 will go here and all these zeros will be here. Again, I'm trying to explain you step by step here, right? After 3, what did you get? We got 9. How will 9 be represented? 0, 0, 1, 0 and 0, 1. Right? So 9 will go into set 1 because these are the set bits, right? These are the tag bits. I'm just breaking it down. I'm explaining you step by step. Okay. So the set bits are 0, 1. So it will go to set 1 and the entry here will be 0, 0, 0, 1, 0 and 9 will be placed here. Cool. Next, what do you have? 7. Okay. What is 7? 5 zeros, double 1. Okay. So here set 3, it will go to set 3. So 7 is present here. Okay. 7, sorry, one second. Somewhere I did a mistake. There should be 1 here, right? 7 is 111. So 4 zeros and 1 because you can't have the same entry here, right? So this is 7. So 7 is also placed here. Next, what do you get? You get 0. 0 is already present, right? Block 0 is already present. So nothing needs to be done here in this case. Then you got 16. So how do you represent 16? 16 is 00 or 00, 100, 00, right? So that's what it is, right? 2 power 0, 1, 2, 3, 4. Yes. So this goes into set 0. So in set 0, you will place 16. This number 0, 0, 1, 00. This will go here, right? Cool. Simple. Next, what do you get? You got 55. So how do you represent 55 now? 55 is 0, 1, 1, 0, 1, 1, 1. Okay. So these are the set bits and these are the tag bits. Now this says set 3. Look at this. This says set 3. But set 3, look at this. Set 3 is completely occupied. That's where your least recently used comes into practice. Look at this. Amongst all this, which is, look at this, between 3 and 7, which is more recently used? 7 is recently used. Okay, which is least recently used? 3. So 3 will get kicked out and 55 will be placed here, right? And this will also get replaced with 0, 1, 1, 0, 1. Okay, 0, 1, 1, 0, 1. So which all, assuming the initial cache did not have any memory block from the current job, what all will be there? Look at this. The most important thing here is 3 got kicked out. So this can't be the answer. This can't be the answer. This can't be the answer. This is the only answer. Now this question can be slightly modified. Somebody could say, hey, what all entries are there in set 1? Okay. Or they can say, in set 1, what are the tag bits? Okay. So this question can easily be modified. That's why I went and explained the more detailed solution. This is a detailed solution, right? There is a shorter solution, which is, first recognize that there are 4 sets, which means 2 bits are needed for sets. Simple. So you have 0 here. Take mod 4 of all of them. That's the set into which it will go, right? And you know it's a two-way set associative. So 0, if you take 0 mod 4, you'll get 0. So this is going to go into set 0. 5, take 5 mod 1, 5 mod 4. So you take mod 4, right? Because you have 4 sets, no? Take mod 4, 5 mod 4 is 1. So this is going to go into set 1. Then you take 3. 3 mod 4 is 3. So this is going to go into set 3. Then you have 9. 9 mod 4, right? So 9 mod 4 is 1. So this is going to go into set 1. It can go into set 1 because set 1 has, it's a two-way set associative. So 5 and 9, both of them can be in set 1. That's not a problem. Then you take 7, right? This is a faster way. 7 mod 4 is 3. So this will go into set 3. Set 3 it can go in because set 3 has only one block. We can place 2 blocks in the 2 lines that are there. Then you have 0. 0 you don't have to do anything because it's already there in set 0. Then you get 16. 16 is mod 0, right? 16 mod 4. Okay, 16 mod 4 is 0. So this will go into set 0. Oh, set 0 there is already one entry present. Second one is also possible because it's a two-way set associative. Then you have 55. Okay, 55 mod 4. What is 55 mod 4? 55 mod 4 is 52. 56 is divisible by 4. So this is 3. Okay, so this goes into set 3. But here comes the problem. Set 3 is already filled. This is in set 3. This is in set 3. Set 3 is already filled. So you remove or kick out whatever was there earlier. So you kick out 3. So the answer here is C. This is a faster way of doing it. But I wanted to show you the more diagrammatic step-by-step way because this question can be slightly modified and you can get a harder question. Okay, so I hope that helps. Cool. Let's go to the next question now. Oh, this is also a good question. Easy. Again, we have only 8 questions today because I wanted to give more detailed diagrams and explanations for today's session. This is a very easy question. If you know how to compute memory access times or average memory access times, this is very easy. The problem with more detailed explanations is we end up solving fewer problems. That's always a trade-off that we have to make. If you want me to explain everything like the previous one, we will not be able to solve more than 5 questions in a day. That's a problem. So that's why in the course videos, we try to give these detailed explanations while when we solve these interactive problems, in 1 hour we want to finish. We're already 36 minutes and we solved only 3 minutes, 3 questions. So that's a problem sometimes that more detailed explanations take more time. And hence we end up solving fewer questions. But let's see. I mean, even if it takes more time, we'll solve all the 8 questions today. It's a trade-off that we always have to strike. In the course videos, we don't have to make the trade-off because time is not a constraint. We can explain things much more coolly, peacefully. We don't have the 1 hour limit to answer 10 questions or anything like that. Okay, cool. People are putting in the answers. Good. Again, put in the best approximation in questions like these because these are all rounded numbers, right? So just put in the best approximation. Yeah, this question is straightforward, guys. Questions like these have been asked for 1 mark in GATE. Somewhat like this. Okay, I see a bunch of you putting in answers. All of your answers are correct. It's a very simple question. You just need to use a calculator, obviously. Please use a calculator for problems like these. Okay, since many of you got it right, C is the right answer and it's very simple, right? So look at this. So how do you compute your average memory access time? First, you go to the cache, right? cache has a 5% miss rate, which means its hit rate is 95%, which means with 95% probability, you will require only one clock cycle, right? With 95% probability. Now with 5% probability, look at this, with 5% probability, you will miss. So in those 5% probability, what happens? You need 200 cycles now, right? Because you're going to main memory, which itself has a miss rate. Look at this, your main memory itself has a miss rate because it has to fetch data from disk, right? So its hit rate is only 92%. So 5% of the chance you will go to your RAM or main memory in this case. Let's call it main memory because it could be a ROM also. So 5% of the times you will go to your main memory. Main memory itself has a success rate of only 92%. So 5% of 92% of the times you will require 200 cycles, right? Sorry, 5% is 1 second. I'm sorry. 5% is 0.05. My bad. 5% is 0.05. Yes, right? Not 0.5. My bad. Just wanted to correct it. Okay, cool. Then, and the disk takes, so what happens now? Okay, the third case, right? 5% of the probability that the cache missed, 8% of the probability that 8% of the probability that your main memory also missed, right? So 5% of 8%, right? This is what is left finally. Of course, you will get the data on the disk. On the disk, you will not have any miss, right? Assuming that the data is present on the disk. So this is 200 plus 1, by the way. So I need to put in 200 plus 1. The reason I need to put in 200 plus 1 here is because first we tried to, because the cache takes one cycle, we tried to find it in the cache. We missed it. That's why we are going to the main memory. So the total time is 201 cycles here, right? So here what happens with 5%, so 5% of 8% of the times, we need 30,000 plus 200 plus 1, right? So if you just get this expression correct, this is just about computing the numbers. So this is 0.95. I pre-computed them. So this whole thing is 9.246. This whole product is 120.80. So if you sum up all of them, 131 is the best approximation for the answer. Okay, simple question. It's 0.05. Yes, I corrected that, right? So very simple question. Okay. So if you know how to, again, this is a very straightforward concept that we have discussed, and it's a very straightforward question, right? Again, some of you are asking this question whether this should be 201 or 200, right? By default, we assume that first we hit. That's a default thing. I think we explained this in the course videos also. First, we always go to cache. If we miss cache, that's a default setup. Unless otherwise specified, the default setup always is first we go to cache. If we miss cache, then we go to main memory. If we miss main memory, then we go to disk. That is a typical standard behavior, unless specified otherwise, right? So that's, again, one of you has this question, so I wanted to clarify that. Cool. Let's go to the next question now. This is a good question. Again, if you draw the diagram, the way we have done in the previous questions, if you draw the diagram, this is very simple. Please draw the diagram. Draw the diagram of your 4-way set associative memory, figure out what is there in tag, what is there in set bits, what is there in offset bits, and break it down. This is a good question actually. I enjoyed it. Again, there was some question from the previous, there is a follow-up question from the previous question that we solved. Thankfully, one of our mentors clarified it. That's what I said, right? It's hierarchical by default, unless otherwise specified. Again, please be patient, draw the diagram, compute all the details. This is a straightforward question. But don't forget to draw the diagram. Okay, I see varied answers here. Okay, we'll see the solution anyway. Please put in your answers. Again, don't be in a hurry. Questions like this you'll encounter mostly for 2 marks. So please be patient and get it right, because getting it wrong will only hurt you. I see 3-4 answers in the chat window. So please recheck your answers. Everyone. Oh, I see more variability in the answers. Okay. Again, please convert this carefully into binary and decimal. Just be careful with that, because some of you may be making a mistake there. So we are asking which set is it mapped to, right? So that's the question here. So the question here is, to which set is this physical address mapped to? So try to operate in binary, because that will ensure that you have lesser errors. Finally convert to decimal. Okay, I see a bunch of answers, but in the interest of time, I'll solve it, because we're already at 7:45. We have done only 5 questions. But anyway, let's go into it, right? So this is your set associative memory. We all know about it, right? So you have a tag and you have your whole stuff. It says 4-way set associative, right? So this is set 0, set 1. This set itself has 4. This set itself has 4 lines, okay, or 4 blocks. Okay, with a capacity of 64 kilobytes. Okay, so the total cache itself is the total memory in the cache that you can store information is 64 kilobytes. Okay, so now what does it say? Each block of 64 bytes. So each block here is 64 bytes, right? Each block here is 64 bytes. Now, how much does each set have? Look at this. How much does each set have? So each set has 64 cross 4, right? 64 cross 4 bytes. Each set, the size of the set, right? Set size. Now, the whole cache itself can store 64 kilobytes of memory. So how many sets will you have? So the total number of sets that you have is 64k by 64 into 4. Okay, let me not make a silly mistake here. This 64 will cancel out. This is 2 power 10. This is 2 power 2. So that will give you 2 power 8 sets, right? Which means you have 2 power 8 sets. So let's make a note of it. So this will be S255, right? So the largest will be set 255. So there are 8 bits, basically 2 power 8 sets, which means 8 bits for the set. So if you now look at the actual address, right? So if you draw the address now, because that's what matters for this whole problem, you have your offset, right? You have your offset, you have your set number, and you have your tag. Now, what does the question say? Your total space is 256 gigs of RAM or main memory, right? So 256 GB. Is anything told about the word size? No, word size, nothing is mentioned. So we'll just assume that one word equals to 1 byte, right? So 256 GB is 2 power 8 into giga, so 2 power 30. Okay, so which implies that this whole length will be 38 bits, right? So this whole thing is 38 bits, right? Because the whole space 256 GB, I mean, this is a more real world problem nowadays because computers have 256 gigs of RAM. or main memory, right? So this is 38 bits, okay? This is the physical address given to you. Now let's break it down, okay? So what will be the offset? Look at this. Each block here is 64 bytes, right? That's what it says. Each block is 64 bytes, which means your offset will be 6 bits. Offset is 6 bits. Your set, you have 2 power 8 sets. So this will be 8 bits. So this is 14. So what will the tag be? If this is 14, this will be 24 bits. Okay, cool. Now what is the question? This is the physical address given to you. This is in hexadecimal. Okay. So it says what is the set in the cache that it has to be in. So look at this. So if you look at this, so let's write this in binary, right? So 0 is 4 zeros. Okay. Then you have 5. What is 5? 0, 1, 0, 1. Then you have 0. So 4 zeros. Then you have A. A is 1, 0, 1, 0. Now let's try to break this thing. So 6 bits will go here. So these 6 bits will be your offset. Okay. So we don't want anything to do with the offset. We don't care. We only care about the set number. The next 8 bits. So 2 bits here, 4 bits here, 2 bits here. These 8 bits is the set number. Right? This is your set number, right? Again, the rest of it, because I only did it till here. There is also this piece which will come in here. So all of that will be your tag. Now what is your set? 1, 0, 1, 0, 0, 0, 0, 1. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 4, 5, 6, 7. Right? So 2 power 7 plus 1. 2 power 7 plus 2 power 0, right? This is 2 power 0. This is 2 power 7. So 2 power 7 is 128 plus 1, 129. So the answer here is 129. Right? So this requires you to draw the diagram, get all the pieces of the puzzle, and then translate this, break it down and assign whatever it is. That's all. This is slightly lengthy. That's why these types of questions like this could be asked for 2 marks. But conceptually speaking, if you know how set associative memory works, this is straightforward, right? From a concept perspective, this is very simple, right? Cool. So let's go to the next question here. Again, problems like the previous one, you can make silly mistakes. So you have to be careful, draw things down, right? Again, some of you are confused about the previous question. This video will be publicly available on YouTube. You can watch it after the session is over also. So I think, again, I've looked at some of the comments. What we have answered is correct. So just think about it. Watch it later. It's very common to do silly mistakes, but just be careful. Okay. You can watch this later. If you think there is an error, shoot an email, we'll correct it. This is a very simple question. Most of you are getting it right. Good, good, good. This is straightforward. Okay, since most of you are getting it right, let me anyway explain this so that we can progress to more interesting questions with more detailed explanations later. So a certain processor uses a 8-way set associative cache of 64. So there is this 8-way set associative. So you have set 0, set 1, so on and so forth. The total cache size is 64 kilobytes, right? So 64 kilobytes is the whole cache size. Okay, what else is given to us? Cache block size is 32 bytes, right? So each block, so one block is 32 bytes. Okay, cool. So it's 8-way, right? So there will be 8 of them here. There will be 8 lines in this. Assume that the main memory is byte addressable. I'm happy they gave it, and uses 32-bit addresses. Okay, so the total address is 32 bits. Okay, so this whole thing is 32 bits. Okay, it has three parts. Obviously, we know that: offset, set number, and tag. Right, set and offset. We know that. Okay, for set associative memory. How many bits are required for the tag and the set index fields respectively in the address generated by the process? Simple. Okay, so look at this. What are we given here? We are given that one block is 32 bytes, right? So which means this will require 5 bits first and foremost. Now you have, to get the number of bits for set, right? You need to know how many sets are there, right? So the one thing that you have to figure out is what are the number of sets. The total size is 64 kilobytes. So 64 kilo by your each block is 32 bytes, right? And you have, it's a 8-way set associative. So into 8. So each set will have 32 cross 8. So this whole thing will be 32 cross 8, right? So the number of sets is this. What is this? 64 is 2 power 6. This is 2 power 10. This is 2 power 5. This is 2 power 3, right? 16 by 8, right? So you get 2 power 8 sets. If you have 2 power 8 sets, you need 8 bits for the set. So if this is 8, this is 5. So this is 13. So you need 13. This is 19. 13 plus 19 is 32. So 13 and 8. So A is the right answer. I mean, this is a simple aptitude problem if you know the architecture of systems, right? So cool. Let's go to the next question. Again, this is also an easy question. Again, somebody has a question. If such questions are actually asked, yes, these questions are marked easy and medium based on GATE standard. These questions are very similar to what you'll encounter for these topics in GATE. There is no point in us giving harder questions. We don't intend to give hard questions also. We have a huge, good set of hard questions, but there's no point in it because such questions will never be asked in GATE. Like if you open up a good standard textbook, if you go to the last problems in the exercises, there are some really good problems there. But you don't need them for GATE. That's the whole point. We're trying to stay at the GATE level. Again, this is not a set associative. This is a fully associative. Okay. Basically associative cache, if you want to think about it. Not set associative. That's what it means. Again, questions like this you can encounter for 1 marks. Guys, please read the question. I think some of you are making this mistake. The question doesn't say how many bits are there in the tag bits. No, it says the memory occupied by the tag bits. Some of you are making that mistake. Remember, tag bits also occupy memory in the cache. Tag bits occupy space. No, the question says the memory occupied by the tag bits in cache. So some of you are making that mistake. You are telling me how many bits is the tag address. That's not what we care about here. Many of you are making that mistake. Read the question carefully. The memory occupied by the tag bits in the cache is. This is not about how many bits are there in the tag field of the address. I see a lot of you putting in the wrong answer. Please read the question. Please, all of you, go back and answer the question again. I strongly recommend you do that. The memory occupied, read the question. I'm highlighting it here. The memory occupied by the tag bits in the cache is dash bytes. This does not say how many bits are there in the address field. It doesn't say that. Again, please, I see a lot of you making a mistake, so please do it carefully. Draw the diagram. This is not set associative, this is fully associative. I see a lot of you putting in the answer which is not correct. So please go back to the drawing board and solve it. I hope I solved it correct when I'm solving it. But anyway, we'll solve it together a little later. The question is, please fill it in bytes. It is only the memory occupied by the tag bits. It is not the total memory of the cache also. It is only memory occupied by the tag bits. That's why I'm highlighting it and leaving it here. Please read that carefully. Only a very few of you got it right till now. Very few. Again, folks, we'll spend probably another 20 minutes on this session. I know there are fewer questions, but we wanted to give you more detailed explanations. So please, cooperate. After this, we have one more question. I want to explain them thoroughly instead of rushing them through. Because these concepts are easy. Yes, now I see some of you getting it right. Good. Please don't jump to an answer. Solve it. Okay, some of you got it right now, thankfully. Okay, you have to read the question very carefully. Let me solve it for you. It's a simple associative cache, right? Okay, so let's draw associative cache. There are no sets in an associative cache, right? What do you have? You have your tag and you have your blocks or lines, right? The data actually, which you fetched from the main memory, right? So on and so forth. So what is given to us? Let's go step by step and see what is given to us. Okay, so first thing that's given is, consider a fully associative cache memory unit with a capacity of 16 kilobytes. So this whole size is 16 kilobytes. The total cache itself is 16 kilobytes, right? Number one is built using a block size of 8 words. Okay, so each block here is 8 words. Very good. The word length is 32 bits. Okay, so let's write down that also. Let me draw it. Let me draw this here. So this whole size is 16 kilobytes. So the next information that's given is one block is 8 words. Sorry, one block is 8 words because B could be confused with bytes. One block is 8 words. One word is 4 bytes, right? So what is the one block in bytes? One block is 32 bytes. So this whole block is 32 bytes. Okay, let's figure out the details. The size of the physical address space is 4 GB. Okay, so let's write down. Where is our physical address space? This is our physical address space. This is 4 GB. So 4 GB is 1 giga words. Look at this. 4 GB is 1 giga words because one word is 4 bytes. Right? One word is 32 bits, which is equal to 4 bytes. So how many addressable words do you have? 1 giga. So this is nothing but 2 power 30 words, which means this address will be 30 bits, right? Now, the memory occupied by the tag bit, let's figure it out, okay? So you have your tag, you have your set number, and you have your offset, okay? Let's fill in these details now, one by one, right? So the first thing here is, there are 8 words here. If there are 8 words in the offset, right? To address 8 words, how many bits do you need? You just need 3 bits. Oh, sorry, this is not set associative, I'm bad, okay, sorry. This is only associative, no? I also made that mistake. This is simply fully associative. Let me not forget that. After drawing set associative for so many times, I'm also making that mistake. Sorry. It's fully associative, right? So there is only tag. There is no set. Okay. There are no sets here, right, in this diagram. So the offset is 3 bits. So the tag field is 27 bits, right? The tag field is 27 bits. Now, if you have 27 bits, so this is 27 bits, this is 27 bits, and so on and so forth. How many sets do you have now? Look at this. How many sets do you have? Okay. So you have, this is total of 16 kilobytes, right? So let's count the number of sets, no? Let's count the number of sets. The number of sets is 16 kilobytes by, not the number of sets. I'm sorry. What am I saying? Sorry. How many lines are there, or how many lines are there? I'm just using the set associative terminology. No, this is fully associative. No, so how many such lines or blocks are there in your cache? This is your cache. No, so how many lines are there? Let's write that down. Right, number of lines is 16 kilobytes by each line. Look at this. Each line has 32 bytes. So 32 bytes. So what will this be? This is 2 power 4, this is 2 power 10, this is 2 power 5, right? So this whole thing is 2 power 9. So the number of lines here, this is line 0, line 1, so on and so forth. You have total of 2 power 9 lines. Each line has a tag. Look at this. Each line has 27 bits of tag. Now what is the question asking us? The question is asking us the memory occupied by the tag bits in the cache, right? Look at this. For each line you have 27 bits. And how many lines are there? 2 power 9 lines are there. So this is the number of bits that are needed to store the tag in the cache. This 27, 27, 27, 27, so on and so forth. So you have a total of 2 power 9 lines, right? So what is this? This is 27 bytes, right? So if you want it in, sorry, bits, this is bits, this is not bytes. So if you want it in bytes, by 8 into 2 power 9. And if you solve this in a calculator, you'll get 1728, which is the answer. Okay. Just remember, just draw this diagram. Look at the question, you have to read it very carefully. I see many of you who made that mistake primarily because you did not read that. This is not set associative, right? So this is fully associative. I got little carried away. So I corrected, thankfully I saw the question again. Again, one of the advantages in drawing diagrams, right? I quickly recognized that there is no set because I looked at, see, the moment as I'm reading the question, I'm drawing the diagram. That helps me a lot actually to correct. Even if I make silly mistakes, I quickly correct because when I'm reading this is something that I follow. When I'm reading the question, I'm drawing the diagram, I'm writing the facts here. So imagine if I thought of this as set associative, I'll see here there are no sets. Oh, then see, that's when I recognized that there are no sets here, and I went back to the question, I recognized it's fully associative, right? Again, here I wrote number of sets, but then I quickly realized, I went to the diagram and I saw, hey, there are no sets, there are only lines. So drawing diagrams and facts helps you avoid some of these silly mistakes also. Okay, cool. At least that's how I avoid silly mistakes. Okay, cool. Sounds good. Let's go to the last question of the day. This is about DMA controllers. Once in a while, you'll get one question on this topic. So let's solve this. Again, if you know how cycle stealing is done by DMA, this is a straightforward question. This is also an aptitude question. If you know the concept of cycle stealing that DMA does with respect to CPU. Again, remember that this DMA is using cycle stealing. That is the important part here. If you know what cycle stealing is, this is straightforward. Lot of times, questions on these topics are given as fill in the blanks because people make silly mistakes. It's very easy to do silly mistakes on this. You don't draw the diagram properly or you don't read the question carefully, you'll make a mistake. Okay, people who know the concept are quickly answering. Very good. This is easy to answer if you know the concept. Okay, many of you are getting the answer correct. Good, good, good. So if you know this concept, this is straightforward. That's what I was telling you earlier, right? If you know the concept, it's a simple problem. Again, concepts like this, you get fewer questions in GATE, to be honest. That's why we put fewer questions here also. Once in a while, you get a question on DMA controllers. Not every time, not every year. Okay, let me go ahead and explain this. Most of you got it right. Very good. So, okay, so you have your DMA controller here, right? You have your IO device here, right? So, what does the DMA do? So, you have your, let's say, main memory like RAM. You have your CPU, right? These are the components that you have, right? Your IO is transferring data at 9600 characters per second, and one character is encoded in 1 byte. So, it is sending data at 9600 bytes per second, right? That's what it is sending. Assume one character is encoded using 1 byte, right? So, the second thing that is given to us is DMA controller transfers 32-bit words in using memory stealing, right? So, it doesn't, so as soon as it gets 4 bytes, 32 bits is nothing but 4 bytes. So, the DMA controller, the way it works is, it takes 4 bytes of information, or whenever this IO device sends us data, it will create the 4 bytes or 32-bit word. And when the 32-bit word is ready, see, the CPU is accessing the RAM and writing, it's running instructions using this. So, what does cycle stealing do? DMA says, CPU, please stop now for a few seconds. I want to transfer the data to the RAM, right? So, but it doesn't do it. So, it only does it once its internal buffer of 32 bits is filled. Otherwise, it won't hijack the RAM. See, the DMA is trying to hijack the RAM and stop the CPU from accessing the RAM, right? So, this is how DMAs work, right? So, now the question here says, the CPU is fetching and executing instructions at an average of 2 million instructions per second. So, 2 million instructions are being executed in 1 second. Now, here comes the interesting part. Look at this. So, 9400 bytes per second. So, it is actually sending 9400 bytes per second. But the DMA is going to send 4 bytes in one cycle. It's going to send 4 bytes in one shot, right? So, so 1 byte, look at this, 1 byte takes these many seconds, right? So, if it's sending these many bytes per second, 1 byte takes 1 by 9600 seconds. So, how much time do 4 bytes take? For the 4 bytes to get accumulated here, how much time does it take, right? So, this takes 1 by 2400 seconds. 4 into this, right? So, once every 1240 seconds, you're going to get 4 bytes of information here, right? And once the 32-bit word or the 32 bits of buffer here in the DMA is filled, it will hijack the CPU, it will hijack the RAM from the CPU and dump the data it wants into the RAM, right? So, what does this mean? This means in 1 second, look at this, in 1 second, this 4 byte buffer or 32-bit buffer is going to be filled 2400 times, right? So, in 1 second, let's see what's happening. In 1 second, the CPU was earlier executing 2 million instructions. See, look at this. Earlier, it was on an average, it's executing 2 million instructions, right? Now, because the DMA is hijacking 2400 times a second, right? Because it is hijacking 2400 times a second, its efficiency will reduce by 2400 by 2 million. Of course, here we are making an assumption because that data is not given. The assumption that we are making here is the time it takes for one instruction to execute is the same time that the DMA takes to write the data to the RAM. Since nothing of that sort is given to us, we'll assume that the instruction takes 1 cycle and the DMA also takes the same amount of time of 1 cycle to write it to your RAM. Since that information is not given. If that was given, we can get more complicated question, right? But since that is not given, what is the question saying? How much percentage the CPU will be slowed? CPU earlier was running 2 million instructions. Now, 2400 of those instructions cannot be executed because the DMA is hijacking the RAM. The CPU has to fetch and execute the instructions and dump them into the RAM, right? So, 2400 times it's not able to run. So, 2400 by 2 million. What will this be? If you simplify it, this is 0.12%, right? So, the answer here is B. That's all there is. So, one more thing, which is one more question that somebody asked about this previous thing, no? So, there is one point that some of you raised. Okay, so let me explain that. Here, some of you got the answer 170, I think. Some of you got in this question, if you recall. In this question, I think the answer was 129, no? So, let me see it in my notes. Yeah, the answer was 129. Some of you got 170 as the answer because you started counting it from here. Again, when you write it in hexadecimal, the first 2 bits here are not useful. So, always, because this zero that is here, right? I can add any more zeros here. I can add any number of zeros ahead of this. Doesn't hurt me. My hexadecimal representation doesn't change. So it is better to start counting from this end. So some of you counted from this end and got the mistake of 170. So just wanted to, because some of you have put in that in the comment section, I wanted to clarify that. Some of you have, because I can put any zeros here, right, on the LHS, on the left side. I can add anything and then you'll get confused, right? So always try to go from this side, right, when you're mapping things. I think 129 was the answer. Some of you got 170 because you started counting from this side. So you have to be careful a little in that case. This option, this sort of question was given intentionally to make you fall for all these traps. Okay. Thank you, folks. Unfortunately, today we could only solve 8 problems. Again, please understand that the more details we go into the solution, the fewer problems we solve. We are always trying to create a trade-off that we want to solve about 9 to 10 problems in 1 hour. It's always a trade-off that we have to strike, because solving too few problems doesn't help, and just spending too much time on the problem, because we assume that people come prepared, right? So any questions that we could not answer because we have already overshot by 15-16 minutes, please reach out to us over email and we'll help you as much as we can. If there is any error that you think we made in these questions, do let us know. We'll correct ourselves. Again, this topic in COA is very easy. If you draw diagrams, as many of you have seen, please draw diagrams, and I mean, it's easy. Let's avoid, I mean, if you draw diagrams, if you write all the facts that are given to you, as we have done, as I have tried to do when I'm solving, you can, this is very, very scoring. If you know the concepts, you can get like full marks in these concepts. These questions look daunting, but they're easy to score, right? So see you next week. As I've just mentioned, we'll start DLD. Okay. So we'll push out the exact syllabus for the Wednesday and Friday sessions. Sounds good. Thank you very much, folks. See you next week. Bye-bye.